Hello everyone, this is Dr. Ritin Kumar, Department of Physics, AJ Institute of Engineering and Technology, Mangaluru. Today I am going to discuss regarding the topic known as laser. So we already know we have came across this laser in day to day life, such as we use the laser in a key bunch, we use the lasers for barcode reading, we use the lasers for the treatment of many diseases, we use the lasers for even decorative purposes, etc. Hence, because let us see now what is this laser actually. So we can see in this topic initially what are the different things we have to discuss in this topic. So first let us see the introduction of laser, next let us see the abbreviations of laser, next characteristics of laser beam, next basic concepts of laser, pumping, types of laser and applications of laser. Okay, so regarding the introduction, so, the basic scientific principle behind the laser was put forward by the scientist Dr. Charles H. Town in 1954. The efforts of several scientists lasers leads to the development of the first laser called as pulsed laser in the year 1960. So basically, what is this laser? Laser stands for light amplification by stimulated emission of radiation. Laser is nothing but actually we have to amplify the light by a process known as stimulated emission of radiation. Now let us see what are the different characteristics of a laser beam. So there are different characteristic of the laser beam. First one, directionality. Directionality in the sense the laser can travel a very long distance without any diverging. So it can reach to a long distance, and because of this property we can measure the distance between distant objects, etc. Monochromaticity, it's of single color. Lasers are generally meant for a monochromatic light, means it is of single wavelength. For example, a helium neon laser which emits 632.3 nanometer, always it all goes on emitting almost equivalent to 632.3 nanometer. So this property is called as monochromaticity. Next is coherence. Coherence, so laser beams are highly coherent. The phase difference between two or more beams is almost zero, or having constant phase difference. So this is another important property of laser. And last one is high intensity. Laser beam are very intense light. It can penetrate to several thickness of any material, thickened material. So it's an highly amplitude or high intense light. So these are actually main four properties of laser. One is directionality, it's a highly directional. Monochromaticity is single color. Coherence, almost all the waves are at constant phase or constant phase difference. High intensity, which can penetrate to a very thick material, etc. So next, when you compare the laser with the LED spectra, we already know that LED, say it is emitting red color light, it is almost looking similar to the laser. So what is that actually means here? So in the helium neon laser, you can see the ultimate line width here. So the ultimate line width, if suppose the laser is going to emit 632.3 nanometer, almost it is emitting, you can see here, it's a clearly visible. The light emitted from the laser is almost near 632 nanometer. But whereas in case of LED, if you see here the LED, it starts from almost like 600 nanometer and it reaches nearly 675 nanometer, a wide band of range. So it looks like a red color, but actually it is not an monochromatic light. Even you can see the yellow color LED, which starts from almost something like 525 nanometer and ends at 650 nanometer. And also you can see the blue LED, which starts at 450 nanometer and reaches at 525 nanometer. So this is the difference between the normal LED light and a laser light. The ultimate line width is very small in case of laser, whereas line width is very large in case of an LED light. So now coming to the principle and productions of laser. First one, the basic principle of the laser is interaction of radiation with matter. So radiation interacts with matter under appropriate conditions. The interaction leads to an abrupt transition of the quantum system such as atom or a molecule from one energy state to the another. If the transition is from a higher state to a lower state, the system gives out a part of its energy, and if the transition is in the reverse direction from the lower state to the higher state, it absorbs the incident energy. In order to understand the manner in which the radiation can interact with the matter, consider two energy states as it is shown in the diagram E1 and E2 of a system. The system may be an atom or a molecule. If the energy difference between the two energy level is delta E, then we know that delta E is nothing but E2 minus E1, that is higher energy state minus the lower energy state. According to the suggestion of Max Planck, if an electromagnetic radiation whose frequency nu is prescribably can be written as nu is equal to delta E by h. We know E is equal to h nu, or delta E is equal to delta E by h, or it can be written as E2 minus E1 by h. So there are three possibilities where the interaction of radiation of matter takes place. That is, absorption of radiation is known as induced absorption, but the emission of radiation is suggested by Einstein 1917 can occur in two principles, either is spontaneous and stimulated emission. No problem. Let us study one by one. Let us see the first one, induced absorption. What is this induced absorption? Induced absorption is the absorption of absorption of the photon by an atom by a system as a result in which system is elevated from the lower energy state to the higher energy state, wherein the difference in energy of the two states is prescribably the energy of the photon. So here the atom absorbs the energy which is present in the lower energy state and get excited to the higher energy state. So the rate of induced absorption, on what rate this absorption depends on? It depends on number of atoms in the lower energy state, that is N1, and it depends on the energy density U nu. You know that if more number of atoms are there in the lower energy state, it absorbs more energy and get excited to the higher energy state. Also, if the energy density is high, then number of atoms absorbs the energy from the lower energy state and get excited to the higher energy state. Hence, it can be written as rate of induced absorption R12. You note I have used the notation 12, that is an atom getting excited from the state 1 to the state 2. Hence, it is written as R12 is directly proportional to N1 into U of nu. Or R12 is equal to, remove the proportionality, introduce a constant B12. So R12 is equal to B12 N1 into U of nu, where B12 is a constant called Einstein coefficient of induced absorption. See, we have taken a constant called B12. So it is B12, atom getting excited from 1 to 2 again here. So it is B12 is a constant called as Einstein coefficient of induced absorption. Next, so spontaneous emission. So what happens? See, the atom got absorbed from the lower energy state and get excited to the higher energy state. So spontaneous emission is the emission of photon when an atom transits or de-excites from the higher energy state to the lower energy state without the aid of any external agency. So what happens in the earlier case, the atom absorbed the energy and got excited to the higher energy state. So in the higher energy state, the atom stands for a lifetime of 10 to the power minus 8 seconds So it can stay in the higher energy state at 10 to the power minus 8 second. After that, the atom comes down by its own from the higher energy state to the lower energy state voluntarily. So there is not required for any energy, or you don't need to supply any energy for the atom which is in the higher energy state to de-excite to the lower energy state. It comes voluntarily after the time 10 to the power minus 8 second. So the rate of spontaneous emission R21, note the notation R21, that is atom de-exciting from the state 2 to 1. So R21 is directly proportional to number of atoms in the higher energy state N2. It is obvious that more number of atoms in the higher energy state, after the time 10 raised to minus 8 second, voluntarily they will come from the higher energy state to the lower energy state. After that they can't stay in the higher energy state, they have to come back to the lower energy state. So that is called a spontaneous emission. Hence we can write atom excited is equal to atom plus photon, the rate equation. So the rate of spontaneous emission R21 is directly proportional to N2, number of atoms in the lower energy state, or R21 is equal to A21 into N2, where A21 is a constant called as Einstein coefficient of spontaneous emission. So A21 is a Einstein coefficient. You can note the notation A21. It is the atom exciting from the state 2 to 1. So it's called Einstein coefficient of spontaneous emission. So last kind of emission is known as stimulated emission. What is this stimulated emission? Stimulated emission is the emission of the photon by a system under the influence of passing photon of just the right energy, due to which the system transits from a higher energy state to a lower energy state. The photon thus emitted is known as stimulated photon, which have the same phase, energy and direction of the movement as that of passing photon, called as stimulating photon. So what happens generally, the atom which is in the higher energy state will last for 10 raised to minus 8 second. After that voluntarily it comes down. Now what we do, we are supplying an energy to the photon to the atom which is in the higher energy state, and stimulating the atom to come down from the higher energy state to the lower energy state. So when the atoms de-excite from the higher energy state to the lower energy state after the stimulation process, they will emit two photons. One photon h nu is the photon which it absorbed earlier to get excited from the lower energy state to the higher energy state. Along with it emits another photon which we use to stimulate it to come down from the state E2 to E1. So one important factor what we have to say in this kind of emission is the two photons. The two photons are in phase. The two photons are in phase, having same and direction of the movement. They have the same phase and the direction. So have same phase, energy and direction of the movement as that of passing photon is known as stimulated photon. So we can write the expression as atom excited plus photon gives atom plus photon, the two photons having same phase and same energy and moves in the same direction. Next, we can study the Einstein's theory of stimulated emission. So this is very important one, the Einstein theory of stimulated emission. So the Einstein proposed that total emission is the sum of spontaneous plus stimulated emission of the radiation. See what the Einstein is going to tell, that see when an atom is exciting from a lower energy state to the higher energy state, there may be a chances of stimulated emission of radiation, or there may be a chances of spontaneous emission of radiation. So he tells that total emission is possible is because of the sum of spontaneous as well as stimulated emission of radiation. So at thermal equilibrium, the rate of induced absorption, see the atoms which goes to the higher energy state is known as rate of induced absorption, that is equal to rate of spontaneous emission plus rate of stimulated emission. For example, if there are 100 atoms which goes to the higher energy state, in that maybe some 75 atoms will undergo stimulated emission process plus 25 atoms may undergo spontaneous emission process. So likewise he has written that at thermal equilibrium the rate of induced absorption is equal to the rate of spontaneous emission plus stimulated emission. So we know already studied that one, the rate equation. So the rate of induced absorption can be written as B12 N1 into U nu, that we have studied here. So it is B12 N1 into U nu is equal to A21 into N2 plus B21 N2 into U of nu. So it can be written as B12 N1 U of nu is equal to A21 N2 plus B21 N2 U of nu. So what you do, you bring this U of nu together, bring that B21 N2 U of nu to the other side. So you take that U of nu outside, hence the equation can be written as U of nu. You take it out, so it is B12 N1 minus B21 N2, that is equal to A21 into N2, or U nu can be written as it is A21 N2 divided by B12 N1 minus B21 into N2, or that is equal to, you take that N2 outside, so N2 will get cancelled out in the numerator as well as in the denominator, so it can be written as A21, and also you bring out one B12 outside, so finally you can see that expression can be written as A21 by B12 divided by N1 by N2 minus B21 divided by B12. So but what is this N1 by N2? So N1 by N2 is according to the Boltzmann factor. So we consider the two energy state E1 and E2 with population densities N1 and N2, and if E2 is greater than E1, then the Boltzmann factor can be written as N2 by N1 is equal to e to the power h nu by kt. We know N is equal to e to the power minus h nu by kt. Similarly, N2 is equal to e to the power minus h nu by kt. You can do that one, and finally it can be shown that N2 by N1 is equal to e to the power minus h nu by kt, or N1 by N2 is equal to e to the power h nu by kt. This is called as Boltzmann equation. So in place of N1 by N2, according to Boltzmann equation, number of atoms in the energy state can be written as e to the power h nu by kt minus B2 by B12. Comparing the equation with the Planck's equation, so U nu is equal to, in place of that one, A21 B21 is equal to 8 by h nu cube by c cube, and B21 and B12 is equal to 1, or that implies B21 by B21 is equal to B12, or the relation connecting various Einstein coefficient. So in order to make the stimulated emission dominant over the spontaneous emission, we require large energy density U of nu. For this, some sort of the feedback is provided by placing two mirrors. This forms of resonating cavity, and small, for this we choose the excited state, a metastable state. Hence N2 by N1 is known as population inversion, and this can be accomplished for pumping mechanism. Which implies actually the probability of the induced absorption is equal to the probability of spontaneous emission. So this is the main thing for laser action. The main thing is, one, you should have large radiation density, and we have to have an metastable state, and in that number of atoms in the higher energy state should be greater than number of atoms in the lower energy state. So these three things are very much essential for getting an laser light or laser action. So students, in the next class we can see what are the laser actions, or different kinds of laser, carbon dioxide laser, semiconductor laser, and applications of the laser, etc. Okay, thank you.